Hey everyone, when will I ever use this? That is my favorite question ever. I get that all the time from the students I tutor, my family, my friends. It's a really good question. I asked it a lot when I was in school and I never got a good answer. I would always get one of two responses because it's in the syllabus, which that's not a reason to learn something. Just because somebody else told you that you have to teach a bunch of people, it's not a reason. That's just carrying forward a lesson. So that was response number one. Response number two was be quiet and listen to what I have to say, which, okay, you're not answering my question. My firm philosophy is that if you have a teacher and they can't tell you why you're learning something, you probably don't have to learn it. And that's not even being a troublemaker and making a problem for no reason. That's being a more educated individual. As a society, we should always question the source of our knowledge and question when will we apply these things. And the unfortunate thing is there will always be a use for all the math you learn in school. And I'm here to tell you what some of those uses are. So we're going to take a trip back to Algebra 2 and talk about some exponential growth and compounded interest. So I always like to tie these to examples that I know a lot of my students will use, and most of my students are either later in high school or earlier in college. So one thing that, of course, they'll be concerned about is buying a car. And if you've ever been to a dealership, you know, in New Jersey anyway, this is not so fun because the salesmen, they're doing their job and I'm sure they're good people, but they're hoping to confuse you. They want to throw a lot of numbers at you and they're banking on the fact that you will get confused and not know what they're talking about because they're salesmen. Their job at the end of the day is to get as much money from you as they possibly can, and they're really good at their job. So I don't want to take money away from them, but I want us to be more educated in our decisions. And here's how you can make a really good choice. I'm going to set up a scenario for you. So here's the scenario. You're buying a brand new car. Let's say the car costs $20,000 and we want to put half down. So we're only going to pay $10,000 today and you're going to finance the other $10,000. So that's the money you would need a loan for. And lucky for us, the salesman will hook you up with a bank. That's not a bad thing. Dealerships work a lot with large banks, and they'll usually have a few different packages, and they'll give you a couple of choices based on how long you want the life of the loan to be. So my question for you is, which is better? Am I better off having an 11% interest rate that we're going to compound monthly? So that means the interest is calculated every single month and then you're paying on that. So usually this would mean you have monthly payments for 3 years. Or am I better off having a 5% interest rate that's going to be compounded quarterly? So let's pretend that you're making quarterly payments for 5 years. This is going to be a simplification of some of the math that will go into it, but here's a good way to gain a lot of basic intuition. We're dealing with some basic assumptions, and we're going to look at some numbers based off of this. So just looking at these, me personally, without crunching any numbers, I don't really know which one is better because you can make a good argument in both cases. 11% is a higher interest rate than 5%. But you're making more payments with the 11%. So I don't know, maybe that'll help dwindle down the principal a little bit more. You have a lower life of the loan with the 11%. The 5% is for 5 years. So without calculating anything, it can be hard to tell. And that's what they're hoping. Even if you think, oh, okay, well, I'm going to say that, I don't know, I don't know, 3 years is a much lesser period of time. 11% seems better for me. Let's say we go with that. There are a lot of other considerations to make, and it's also hard to answer the question, okay, but how much better is it? That's where we need some math. So we're going to use a formula I'm sure you've come across in Algebra 2. It's a variation on exponential growth. The equation we're going to use is a equals p times 1 plus r over n to the power of n times t. This is where a is your accumulated value. This is how much money you'll end up paying, because we know when you borrow $10,000 from a bank, you're paying more than $10,000. You got to pay that interest. A is going to have the 10,000 plus the interest. P is going to be the principal. In this example, it's just $10,000 because that's the number you're borrowing. You're going to end up paying more, but that's how much you're asking the bank for. And you're paying more because they're lending out money and taking a risk. So they want to be paid for that risk. There's nothing wrong with that. Interest benefits everybody. R is going to be your actual interest rate. So in one scenario, it's 11%. In the other scenario, it's 5% or 0.11 and then 0.05. N is the number of compounding periods. This is actually talking about how frequently interest is being calculated. We're also going to call it the frequency with which you're making payments. Those two don't always have to be the same thing, but that's another video for another day. We're going to assume every time they calculate interest, you're making a payment when they do that. And then finally, T is going to be the full time period. In this case, for one scenario, it's 3, the number of years. In the other scenario, it's 5, the number of years. It doesn't have to be years, but we're going to say that it's years. So here's the logic behind this formula. We're saying that the amount you'll end up paying, A, is equal to the amount you're borrowing, P, multiplied by this 1 plus R over N. What the 1's doing is it's saying I'm keeping the 10,000. I worked at Dunkin' Donuts for like 6 years, and the register would always calculate sales tax. So when you buy a $3 coffee, you pay more than $3. Let's say sales tax is 7%. The way the computer or register calculates it is they take $3 and multiply it by 1.07. The 1 is saying you're still paying $3. The 0.07 is saying add on 7%. That's what this 1 plus R over N is doing. 1 is saying keep the 10,000. R over N, well, R is the interest rate, but we have to divide it up over how frequently we're calculating it. So you can think in the first scenario, I'm taking that 11% and distributing it over the entire year based on each month. So I'm distributing it monthly. Raising it to the power of N times T is just the number of times you're going to apply it in total. You're not going to apply in either of these scenarios. Since we're doing it for 3 years, you're not just going to apply interest 3 times. No, you're doing it every month for 3 years. So you're doing it 36 times because there's 12 months in a year and there's 3 years. So 12 times 3 is 36. In the second scenario, it's quarterly. So every 3 months for 5 years. So there's 4 quarters in a year. You're doing it for 5 years. That's 4 times 5, which is 20. So that's what this formula is saying. In these scenarios, through the power of math, I calculated each of these already. The first scenario, if we borrow and finance $10,000, the total amount you'll end up paying is $13,888.79. And I got that just by plugging in these numbers. I said that P was 10,000. I said that R was 0.11. I said N was 12 and T was 3. For the second scenario, I also just used this formula and plugged in a bunch of numbers. I said P was 10,000, R was 0.05, N was 4, and T was 5. And the number that you end up getting there is $12,820.37. So it turns out the better deal for you, the buyer, is the second option. This is what is better off for you. And I know you might be saying, well, okay, it's only like a $1,000 difference. Is that really a big deal? Well, yeah, $1,000 isn't just a small amount of money. That is going to be your first major service. If you're buying a new car, that will pay for your 30,000, 45,000, your 60,000 mile service. 60,000 miles is like a $1,500 bill in New Jersey. That will basically pay for most of it. And if you throw that money in a bank, invest it, for a couple years, when that time rolls around, you'll be able to pay for that and not even have to worry about it. So it is very significant. One valid question is, what if I took this exact same scenario, but I just swapped the interest rates? So in the 3-year scenario, I'm going to have a 5% interest rate. And in the 5-year scenario, I have an 11% interest rate. How would that work out? Well, the way that works out is in the 3-year scenario, you're going to end up paying $11,614.72. And all I did was I switched out 0.11, 11% for 0.05, 5% in this same formula right here. That's like a $2,200 difference. That's pretty significant. That's 2 major services paid for. In the 5-year, now this, I swapped 5% for 11%. Now we're paying 11% interest. This goes up to $17,204.28. You're paying almost double what you borrowed in the first place with an 11% interest rate. And that's not that crazy of an interest rate, especially if you don't put a lot of money down. We see this number jumped up by about $4,500, and that's a lot of money. That's nothing to sneeze at. So even using this really simplified formula, again, there are more complicated scenarios. You can do more involved math, but we'll save that more involved stuff for another day. A 17-year-old using this formula you learned in class can make some pretty informed decisions and save a lot of money in the long run. The last thing we can talk about is effective interest rates. Effective interest rates are basically asking the question, if I were to pay 6% every year, so 6% annual interest, what would that be on a monthly basis? That's a good question to ask. The way you would calculate that is the interest rate in question, we'll call it R star, is equal to 1 plus R over n to the power of n times t minus 1. And we can see a lot of similarities with this. Basically, the assumption this is making is we're just converting from one to the other, but adjusting for how frequently we're calculating the interest and how many times you're applying it. So let me throw a scenario at you. Let's say they tell you that you will pay 6% APR monthly for 5 years. What would that be? Let me clarify the question. They're telling you you're paying 6% APR. APR means annual percentage rate. That means you're paying 6% interest per year. The question is, if I want to figure out what I'm paying on a monthly basis, how much interest am I being charged on a monthly basis, and I have a loan for 5 years, what would that interest rate be? Well, plugging in all this stuff, I'm going to let R star be 0.06. N is 12 because we're calculating it monthly, and T is 5. Because the one thing I don't know is what the effective interest rate was, what R is attached to the monthly rate. This ends up telling you that R is going to be approximately equal to 1.17%. So that means if I were to take a 1.17% monthly interest rate and pay that over 5 years, that's the exact same thing as 6% APR. And this just goes to show how deceiving these numbers are. Who would have thought that? I think that's sort of counterintuitive, but the math speaks for itself. So in summary, here's everything we're dealing with. We can see that using these simple formulas that you learned in high school math class in Algebra 2 actually have some real world ramifications, and there's some really powerful tools. I hope that you feel good about everything that we talked about. If you have any questions, throw them down in the comments. Tell me what else you want to learn about. I am really looking forward to continuing to create a more educated future and help people learn about the things that they're involved in and just see how the math that you learn can really be used on a daily basis. Thank you for your time, guys, and I'll catch you later.